Now that we have learned how to solve radical equations, we're ready to learn how to solve equations with rational exponents. Now, you might not believe me, but fundamentally, you already know how to do this. We've solved radical equations, and rational exponent equations are the same nature, but they have different notation. So before we solve the equations, let me show you the connection between a radical expression and a rational exponent. If I have the nth root of some number raised to the mth power, we say this is a radical expression. We can rewrite this with a rational exponent. So the nth root of a to the mth power is equivalent to a to the m over n power. The word rational basically means fraction. So we're going to be looking at equations with fractions in the exponents, and by the formula that I've written here, we can see that a rational exponent expression is the same thing as a radical expression. They just have different notations. Now, understanding that and knowing that you already know how to solve a radical equation, we're going to follow fundamentally the same process. For example, if I gave you the very simple equation, square root of x equals 3, would you know how to solve it? I hope that you said, sure, let's square both sides. So to solve an equation like this, I am going to square both sides. The reason we square both sides is to cancel the radical. The square root of x squared is x, and we have easily solved the equation. Now, I'm going to give you the exact same equation, but this time using rational exponent notation. Using our guiding formula on the left and looking at our square root expression, notice in the square root of x, there's no index. That is, there's no number right there. If there is a missing number, we understand that the index of the radical is 2, or we're dealing with a square root. Also, there's no outside exponent listed, so I can assume it is 1. So I can write this equation as x to the 1/2 equals 3. The index of the radical, which is 2, is now the denominator of my rational exponent, and the outside exponent is now the numerator of my rational exponent. So the equation square root of x equals 3 is the same as the equation x to the 1/2 equals 3. They're just written with different notation. Now, if I know how to solve the radical equation, I'm going to apply that same process to my rational exponent equation, and I'm going to obtain the same answer. Notice on the left, we have a power raised to another power, and just to remind you of that exponential rule, if we have a number raised to a power and then raised to a successive power, we multiply those powers. So on the left of our green equation here, we have the power 1/2 and the power 2. We're going to multiply those powers. 1/2 times 2 is 1. So we get x on the left, and 3 squared on the right is 9. So fundamentally, if you know how to solve a radical equation, we're going to be applying the same principles to solving rational exponent equations, but again, the notation is just a little bit different. So let's go through the process, or the algorithm, for solving a rational exponent equation. Step 1, we're going to isolate the expression containing the rational exponent. Sometimes that's already done, and you'll be able to skip that step. But relate this back to what we know about radical equations. Remember, to cancel the radical, first we have to isolate the radical and then square both sides. We're doing the same thing here. Isolate the expression containing the rational exponent, and then step 2, we're going to keep this very general so that we can deal with exponents other than 1/2. Step 2, raise both sides to the reciprocal of the rational exponent. Sounds a little different than squaring both sides. But if we come back up here to our example, we were squaring both sides. why were we squaring both sides? Because 2 and 1/2 are reciprocals. The product of a fraction and its reciprocal is always 1, and that's how we're going to be able to cancel the exponent. Now, in stating it like this, we'll be able to handle exponents like 2/3 or 4/5, exponents other than just 1/2. Once we raise both sides to the reciprocal of the rational exponent, then we may have to solve the resulting equation. It may be linear, it may be quadratic, it may already be solved, but at that point we will solve. Now, we do need to add a step 4. Can you guess what I'm going to write for step 4? What's always our last step? Check. We're going to check by substitution with our calculator. So this process is very similar to solving a radical equation. We're just dealing with different notation, and maybe it's a more general approach. So let's practice this algorithm on our first example. Example 2a, solve the rational exponent equations. The equation is x to the 5/4 equals 3/2. Notice the rational exponent part is isolated. So we are ready for step 2, where we raise both sides to the reciprocal of the rational exponent. So I'm going to raise both sides to the 4/5 power. Now, be careful that you write the 4/5 in the exponent on the right. That's not 32 times 4/5. This is 32 raised to the 4/5 power. So be careful how you write it so that you interpret it correctly. On the left, we have one power raised to another power, so we know we're supposed to multiply those powers. 5/4 times 4/5 equals 1. So we have x to the power of 1, or we can write it more simply just as x. Over here on the right side, we have 32 to the 4/5 power. We need to evaluate this. To evaluate this, I'm going to rewrite this in radical form. So the base of the exponential expression becomes the radicand, or the number that lives in the house. The denominator of the rational exponent becomes the index of the radical, and the numerator of the rational exponent becomes the outside exponent. So in order to evaluate 32 raised to the 4/5 power, we can think of it in radical form, the 5th root of 32 to the 4th power. Now, let's evaluate what's inside parentheses first. The 5th root of 32 is 2, because 2 times 2 times 2 times 2 times 2, or 2 multiplied by itself 5 times, gives us 32. So the 5th root of 32 gives us 2, but we still need to raise 2 to the 4th power, and 2 to the 4th power gives us 16. So the way we evaluate those rational exponents is by converting them to radical form. Now, before you panic, we can go straight from this step to this step using our calculator. To evaluate 32 to the 4/5, we'll type in 32 and then the caret or exponent key, and we'll type in exponent 4 divided by 5. When we press enter, we obtain a value of 16. So I wanted to show you how to convert the rational exponent into a radical expression so you'd get an understanding of what does 32 to the 4/5 even mean. It represents a radical expression, but the value we're after here is 16. Now, let's check our original equation. So I'm going to go all the way back to the first equation, and I'm going to plug 16 in for x, and I'm going to make sure that I get a balanced equation. Notice 16 to the 5/4 equals 32, so we can be confident that we have solved the equation correctly. Let's try another one. X minus 3 to the 2/5 equals 4. Our first step is to isolate the expression containing the rational exponent, and that is done in this case. So our next step is to raise both sides to the reciprocal of the rational exponent. So what power should I use on this equation? I bet you said 5/2, right? Because that is the reciprocal of 2/5. Now, the left side is easy. 2/5 times 5/2 is 1. The exponents cancel, and we get x minus 3. Now, there's something tricky that happens on this one. So far, we have done everything correctly. But if we'll remember the connection between rational exponents and radical expressions, notice what we have here is a 2 in the denominator. that represents the index of a radical. So actually what we're doing here is taking at least a form of the square root of both sides. Why is that important to know? Well, we learned in our square root property that when we take the square root of both sides, we get one positive and one negative answer. Now, we didn't do that on example A because the denominator was an odd number. When you take the cube root or the fifth root or an odd root of both sides, you don't need the plus or minus. But on this example, because the denominator was even, we do need that plus or minus. So that's pretty sneaky. Sometimes I forget about that. I hope you don't forget about it. But we've got it here where we need it. Now for practice, let's evaluate this by converting to radical form. So the 4 becomes the radicand. The denominator of the fraction is the index. You don't have to write it, but you can. Remember, if you don't write it, it indicates a square root. And the numerator of the rational exponent becomes the outside exponent. So evaluating with the correct order of operations, we start inside parentheses. The square root of 4 is 2. And 2 to the 5th power is 32. This has led us to a linear equation, so I still need to do a little bit of work to solve for x. In particular, we need to add 3 to both sides. And I'm going to sneak 3 in front of that plus or minus 32 just to make it a little bit easier to read. Now, I'm going to separate these two answers. We do have two answers. One is 3 minus 32, and the other one is 3 plus 32. So evaluating those, we get x equals negative 29 and 35. So this one yielded 2 solutions. Now, we want to make sure that neither of those is extraneous, so we're going to plug both of those solutions, starting with negative 29, back into the original equation where I see the x, to check for a balanced equation. So here's what it looks like when we plug in negative 29. The calculator yields a value of 4, and that's what we had on the other side. So we have done it correctly. Let's evaluate. Let's plug 35 in for x and evaluate. Well, that one yields 4 as well, so it looks like both of our solutions are correct, and we've got 2 solutions. Okay? Now remember, when do I need to use the plus or minus? If I raise both sides to a power where the denominator is even. And again, that's very easy to forget. Let's try a couple more examples. X to the 2/3 equals negative 16. So step 1, we're going to isolate the term that contains the rational exponent. In this case, that means we need to add 16 to both sides. Then we will raise both sides to the reciprocal. Reciprocal means flip it over, right? The reciprocal of the rational exponent. On the left side, we multiply the powers to get 1. And on the right side, we need to evaluate 16 to the 3/2. For practice, hey, by the way, do we need the plus or minus in this case? We do need the plus or minus. I almost forgot about it. Did you see that? Because the denominator is even, that means we are taking the square root of both sides. So we need to evaluate 16 to the 3/2, which means the square root of 16 cubed. If you were a little concerned about how am I interpreting the plus or minus, notice here when we go from the rational exponent notation to the radical form, we can see there's a square root there. So we have taken the square root of both sides. Now, let's evaluate the square root of 16 to get 4. And 4 cubed is 64. But again, remember, as I said earlier, don't panic, because we can go straight from rational exponent to value using our calculator. So I'm going to type in 16 raised to the 3/2 power to verify we do get 64. And because we have the plus or minus, we still need the plus or minus there. One thing I want you to note right here, make sure you understand that is not 16 times the fraction 3/2. It is 16 raised to the 3/2 power, so make sure you evaluate it that way with your calculator, and be careful to write that 3/2 exponent high enough in the exponent so you don't accidentally interpret that as multiplication. Now, we need to check both of our answers. I'm going to start with the positive 64. We're plugging this into the original equation for x. Now, right here, I have 64 to the 2/3, but I'm going to use my right arrow key to get down out of the exponent before I type in the minus 16. Looks like positive 64 is a solution. Next, we'll check negative 64. But we have to be careful with our syntax. We want to make sure that negative 64 is raised to the power of 2/3. That means I have to put the negative 64 in parentheses. And when we evaluate, we also get 0. So this equation also has two solutions, positive and negative 64. One more example for this section. We know our first step is to isolate the expression containing the rational exponent. In this case, I have 2. So what I'm going to do is add this entire term over to the right side. We have 2x plus 5 to the 1/3. Adding this big term to the other side, we get equals 6x minus 1 to the 1/3. Now in this case, because both exponents are the same, we can raise both sides to the reciprocal of the rational exponent, which is 3. So essentially, we are cubing both sides. When we cube both sides, 1/3 times 3 gives us 1. Both of our exponents are going to cancel, and that leads us to a linear equation from Unit 1. Our goal in solving a linear equation is to collect all of our variable terms on the left. So I'm going to start by subtracting 6x from both sides. That's going to get all the variables to the left. And then subtract 5 from both sides. That'll make all of our constants land on the right. And we have the equation negative 4x equals negative 6. We will finish by dividing both sides by negative 4 and reducing. And our answer looks like x equals positive 3/2. Let's be sure that this is the correct answer. Get in the habit of checking your work with your calculator, and you'll be able to catch mistakes. If you find some sort of imbalance when you plug it in, that would prompt you to go back and work the equation again. All right, 2 times 3/2 plus 5 raised to the 1/3 power. Use my right arrow key to get down out of the exponent. Minus, remember, I'm keeping my eye on the original equation, and I'm plugging 3/2 in for x. We are looking for a value of 0, and we have obtained a value of 0. So rational exponent equations are related to radical equations. They just have different notation.